continuing with our second part of the video, where we are going to generate a sine wave model and forecast using LSTM. As you can see on the screen, LSTM stands for long short term memory neural network, and the LSTM model which you have created can be tested using a noisy test input, and it looks at the input number and forecasts it as a sine wave so that you can get a cleaner sine wave. Now we are going to discuss how to build or create the sine wave model from the data sequence which we have created in the last video, and how to train the model, and how the samples were created, that were also discussed in the first video. Then how to save the sine wave into a CSV format, and also how to save the trained LSTM into an H5 format so that it can be used by other models. The principle is the program uses special RNN called LSTM, which are designed to capture and learn patterns in the sequential data. Now, there were some basic videos on this in the earlier videos. Now, a window of past values from the generated data is used to train the LSTM model, and then the trained model is used to predict the next value in the sequence. Now, the complete program to build the model, LSTM model, that is what we are going to discuss here. So in continuation with the earlier video, you may also see the earlier video where same libraries are used, Keras library. Then the first thing we have to do is initialize the LSTM model with splitted samples. So in the last video you must have seen, if we have 390 rows of data, each of having a window of 10, that means you are indirectly creating a 390 by 10. That means each row having 10 different data, and 390 such rows are sequenced, and this is nothing but the sine wave samples time shifted in a group of 10. Now, while building any LSTM model, some of the most critical hyperparameters to be considered are: number one, the number of LSTM layers. See, you cannot simply randomly choose the number of LSTM layers. You have to, a large number of layers, the increased numbers, can help capture more and more relationships in the data, but can also increase the risk of overfitting. The second one is number of LSTM units. It's called units is equal to 50, like that. Increasing the number of neurons can help the model capture more and more complex patterns of data, but can also increase the risk of overfitting. An activation function, there are sigmoid, ReLU, etc. Or it could be tanh also. Tanh goes from -1 to +1, sigmoid goes from 0 to 1. Now, dropout rate is actually a regularization technique that can help prevent overfitting. It helps, it specifies the fraction of the input units to drop during training. The learning rate is very, very important. The learning rate determines how much the model weights are updated during training. A larger learning rate can lead to faster convergence, but can also cause the model to overshoot the minimum. So, a minimum learning rate with the optimum learning rate is what is required. Batch size. It determines the number of training examples that are used in each training iteration. Larger batch size can lead to faster training, but can also lead to slower convergence and poorer generalization. The epochs. The number of epochs is, it determines the number of times the model will be trained again and again on the same data set. It's important to choose an appropriate number of epochs to prevent overfitting or underfitting. Now, this is how you define all this. It's a sequential model, and units is equal to 50. That means number of neurons is 50. So input shape is what we have got from the earlier videos. So you remember X. The X in shape 0 was 390 and X in shape 1 was 10. And model dot add dropout is 0.2 and units is equal to 50. Again, this is how you define all these things. Now you come into the real model dot compile. You are using an optimizer called Adam and you are using MSC, mean square error, for loss function. And you are now having an input X in with a 390 by 10. You know that 390 rows and 10 columns. And history is equal to model dot fit arguments with X in and next X. The next X. These are all X in and net X was. This is a sampled data formulated in a group of windows. Actually, you must have seen in my earlier videos. Epochs is equal to 50, batch size is 50, and verbose is equal to 1. And now the training starts. After training, it might take some time for it to train, and you simply plot the results. You can see that upon training, it gave some results. So you can see at the bottom, actually the loss is less than 10 to the power minus 2. So the learning rate which is chosen is good enough so that it has reached, it cannot go to 0 but can be close to 0. So now whatever data we have actually in the sine wave data, you would like to store into a data frame. So you are storing into a CSV file. And now the last part comes actually when you suppose you would like to port this model in a single file instead of having the entire program taken along with you. So the hierarchical data format version 5, it's called HDF5, is a file format that is designed to store large amounts of data, model architecture, parameter weights, and the other information about the machine learned models. So it also creates an H5 model in this video using this command model.save and .h5. And further, this video, so you covered how to build or create a LSTM sine model, how to train that and save into a CSV file or save the model into an H5 format. Next video, we will use this model to predict on a noisy testing data and plot the output. And this is how the output you will expect in the next video. You give a noisy sine wave into the good model, it brings out the red ones from that. So for example, suppose you have very noisy data, you can first predict it and it looks like a sine wave. One more time if you predict, even it becomes more and more cleaner. So all the details about this program installation etc. are in the description box. Thank you.